Okay, so we are basically talking about nucleus structure or the structure of the atomic nucleus, right? Now, you have already studied in your graduation as well that when we start with nucleus structure, what's the first thing which comes to mind?
Spherical.
Spherical shell model, right? Then we have got the liquid drop model where we have got the Bethe-Weizsäcker mass formula, right? So there are so many things. Then we have got the Fermi gas model, right? Then rotational model, one of the most famous models, right? Now the thing is that, have you ever wondered why are there so many models? In a way, it's a good thing. There are so many things to study. But again, it's a bad thing. Why are there so many models? Why not just one model and we just try to explain everything? Isn't it so? Why are there so many models? This, in fact, tells you about the richness of the atomic nucleus. I mean, to say that the atomic nucleus behaves in such a way that there is hardly one model which can explain all the features of it. Actually, there is one model, that is the shell model. It can explain all the features, but for that we have to use very sophisticated methods which are most of the times very difficult due to computational issues and also because of the inadequacy in knowing the nuclear interaction. Two very important things. Okay. So basically in nuclear structure it is very important that we have nuclear models. There you can sit over there. Okay. So because as I was saying, there is hardly any model which can explain all the richness. That's why we have to resort to various nuclear models. And when I am saying various nuclear models, as you will see, there are various reasons for choosing such various models. Okay. Now, say for example, in the class, I just say, start singing. In this class, right now, most of the students, they feel shy, they will not sing. Suppose one particular fellow, he starts singing, okay. Only one person sings. There is a possibility that two or more people sing, right? Again, when they sing, they may not sing the same song. They may be different type of songs. And there is a possibility that all of them start singing. And when they sing, they are singing the same song. So you see, there are so many varieties, so many possibilities. Same in the nuclear structure, models also, we have got various models depending on the scenario. Say for example, you already know about the magic nucleus, right? That is the nucleus whose shape is almost spherical. Okay, and what? Any excitation apart from that is very simple to explain. We have talked about this. This is where the domain of the spherical shell model lies, the importance. Okay, now, so there are various possibilities. One is using mean field, or you can say microscopic approach. What is that microscopic approach? Microscopic approach is basically, we have got a nucleus, well, there are so many nucleons inside, right? Now as a student of physics, why not write down the Hamiltonian, containing all the kinetic energy, all the potential energy, right? All the interaction terms, right? So this is basically the microscopic approach. You have seen that how we derived the various truncation schemes in the shell model. So in fact, the spherical shell model is one of the microscopic approaches. Okay, where we write down the entire Hamiltonian and from the very microscopic details. Another way is your macroscopic approach. Say for example the liquid drop model, the Bethe-Weizsäcker mass formula. You consider liquid drop model what? It's the same old nucleus, right? But now you are not considering the individual aspects. You are not considering the individual nucleons, but you are considering the bulk structure. You are considering a bulk nucleus with mass m, radius r, volume v, and all that. Okay. So you are considering the entire collective behavior, as if all the nucleons are behaving collectively. There is no individual aspect. Say for example, when we go to a football stadium and people are cheering, Mexican wave, say for example, they start doing Mexican wave in waves, right, in circles. When there is a Mexican wave going on, will you be able to identify the voice of one particular person? No. It's a chaos, almost. Collective behavior. Okay. So, this is like that. So, there are scenarios where a nucleus, now when I am saying a nucleus, I am saying a general nucleus, not a single nucleus. Okay. Because a particular nucleus can behave like to have a single particle, like a single particle structure. It can have like that. I am talking about some other nucleus which behaves in a collective way, right? So don't think I am talking about one particular nucleus. Now there are scenarios when one particular nucleus can behave differently. We will talk about it later on. So this is the microscopic approach. Now there is yet another approach which takes in both of the techniques. And what is that? It is the unified approach. Can you give me an example of unified approach? See, in the last class we talked about the asymmetric harmonic oscillator, right? So what was there? Basically, we have got the deformed core and a few nucleons, maybe one nucleon outside the core. Now when I am talking about deformed core, basically I am talking about the collective aspect. All the nucleons inside the core, they have actually deformed the core. But again I am talking about a single particle outside the deformed core. So it's a microscopic approach. So it's a marriage of both microscopic and macroscopic approach. That's why it's called unified approach. So the anharmonic harmonic oscillator problem that we discussed in the last class, this belongs basically to this unified approach. Other models like Nielsen model, which is sort of extension of this anharmonic oscillator model, this also belongs to the unified approach. Okay. So there are so many types of variations out there. Any question? I am just talking about the various important classes. Now there is another very interesting approach. Let me point it out over here. This macroscopic approach here, which is the liquid drop model, right? Here, this is basically important for explaining. Now I am using a different color. This approach basically explains the collective behaviors of nucleus. Okay. The microscopic approach, on the other hand, the shell model which belongs to it, this can single particle behavior. This can explain along with collective behavior as well. This is also, you can say, a collective plus single particle. Yes. Collective ki kore hocche, how is it possible? Collective. Now in microscopic approach, we have talked about shell model, right? When we talked about shell model, I talked about one particle outside the core. I talked about two particles outside the core, right? Now it can happen, I talk about 5 or 6 particles outside the core. Now the moment there are so many particles outside the core, think of it like that. We have got a core like this, and if there are few nucleons outside the core, it is not that all the nucleons will be distributed equally. At one time they will fall like this. So you can think of it like that. Now the core becomes deformed like this. Think of the density distribution, matter distribution like this. So this is the reason for deformation of the core. And then we will be talking about, when I am talking about so many nucleons outside the core, I am in the regime of shell model, but actually I am talking about this deformed case. So if I consider all the various possibilities of excitation, given I know about the nucleon-nucleon interaction between them, then the shell model will be able to perfectly explain the collective behavior in that case. It has been seen, it has been observed. So keep this in mind. Most of the books, they say that shell model, they explain only single particle behavior, which is absolutely wrong. Okay. Now there is yet another class. Say for example this macroscopic approach. Okay. Here I am talking about this collective behavior. Okay. There is yet another class, and when I am talking about this liquid drop model, these are basically a group of geometry collective models. Why? Because here I am talking about geometry as well. Say for example, I have got a spherical nucleus. Look here everybody, I have got a spherical nucleus. Okay? Now we have talked about the shell model, features, one nucleon outside this. We have talked about this. Now suppose I am telling you that this entire spherical nucleus has collective excitations as well. Now tell me, what will be the possible collective excitation of this spherical nucleus? Can it have rotational structure? Consider a very simple thing. You have got a sphere, uniform sphere. Now you just start rotating it. There is no light shining on it. Will you be able to identify whether the sphere is rotating or not? No. There is no way to understand if the sphere is rotating or not. This means that the sphere, in a way, it cannot have rotational structure. The only excitation possible for a spherical structure is vibrational, like this. Vibrational structure. This is important, keep this in mind. Okay, vibrational structure. Yes, again. Okay. So what I am saying is that consider a very perfect sphere ball. Okay, I am asking you, is it possible that it has rotational structure during excitation? Rotation means deformation, right? Now if I put the ball on a sphere, on a plane and rotate it and no light falls on it, you will not be able to identify whether the ball is still or it is rotating. This means that it is not possible. I am just saying differently. It is not possible for a perfectly sphere structure to have rotational states. For rotation you need deformation. I mean the core should be like this, so that when it rotates you will be able to understand. Like an egg, you rotate it, you will be able to understand the egg is rotating. Why? The egg is deformed. By default it is deformed. Okay. So a perfectly spherical nucleus, during collective excitation, it will exhibit vibrational excitations. Now what are the vibrational excitations? We will talk about it later on. But I am just now talking about the general class. Okay. Now, so geometry collective model. Why geometry? Because this excitation, you see, there are so many types of excitation. Let me just tell you. Okay, write it down. This is also important. Now, vibrational structure. The most basic vibrational structure is, there are two aspects, think about it. One is shape, another is density. Okay, let me just draw this. Okay, so vibrational excitation. What I am saying is that there are two very interesting structures. Spherical nucleus I am considering. Now it is important to remember that a deformed nucleus will have rotational structure, right? Also it can have vibrational as well. But a perfectly spherical one will have only vibrational structure. Now let me just talk about the vibrational structure right now. So you see, it has got a shape, right? Now it has also got a density as well. Now it can happen that the shape remains fixed, but density fluctuations are there. What will it look like? Then it will look like this, as if yes, it is going like this and then coming up like this. You understand? Like this. So this is known as breathing mode excitation. Where the shape remains fixed but there is density fluctuation. Now tell me, in the excitation spectrum, where shall this breathing mode lie? Will it lie in low energies or little bit higher energies? Think carefully. Nuclear matter is compressible or incompressible? If it was incompressible, I would have easily crushed this chalk. Okay. It is incompressible. What is the reason for supernova explosion? When during the death of a very massive star, the core, it is unable to withstand the gravity, everything collapses, right? Now when they start collapsing, then in the center there is something called neutronization going on. All the stuff, it is being converted to neutrons, right? Now all the neutrons, they will keep coming to close to each other. Then there will be a time when the neutrons will start touching to each other and the overall envelope will even start to crush it. But since nuclear matter is incompressible, it will not be able to crush. So as if think of it like that, a train is coming at very high velocity and it hits a mountain. What will happen? Nothing will happen to the mountain. The train will just rebound, accident. So supernova explosion is like that. Entire envelope, it gets rebound, it blows up. Okay, so this is one of the very important aspects which tells us that nuclear matter is incompressible. So here also, I am talking about density fluctuation. I am talking about the fact that nuclear matter is slightly compressible. So this means that this will require very high excitation energy. So this you will not observe, this breathing mode of excitations, you will not observe in low energy. It will be in somewhat higher energies. Okay? I am just telling you everything from very basic physics point of view without going into the mathematical details. Now, yes. Incompressible, but again, slightly compressing. It's not that it's like going like a black hole. It's entirely collapsing to a point. Slightly compressible. Okay. And why incompressible? Because of the hardcore potential of the nuclear-nuclear interaction. Strong interaction is very nice if you are very If you are within the range, you are most welcome. But it doesn't mean that you can come and we can have a perfect union. No, there is a hardcore potential. You will be coming, so you can come, and then there is a certain region within which you cannot enter. Okay, now, so this is a very basic breathing mode, vibrational excitation, and remember this is observed in high energies spectrum. Now, let me talk about another very basic structure. So now I will be talking about low energy excitation somewhat. So density is fixed, and let me then talk about shape fluctuations. Now there are so many possibilities of shape fluctuation. First possibility, what are the constituents of the nucleus? Proton and neutron, right? Now it is possible, I am talking about a perfectly spherical nucleus, remember. So it is possible that the protons and the neutrons, they are oscillating. This is the proton center of mass and this is the neutron center of mass. They are oscillating, protons and neutrons together. You see, this is also a collective excitation. The protons as a whole, the neutrons as a whole, they are oscillating with respect to each other. This is one possibility. Another possibility is prolate structure, oblate structure. So the nucleus goes from spherical to prolate to oblate structure. This is another possibility. There are so many types of possibilities I am showing you, and these are observed at lower energy compared to the breathing mode. I will tell you the exact names later on, but just try to understand what the various possibilities are. Prolate and oblate shape. So I mean to say the entire shape in equilibrium is spherical, but as a result of excitation it can become like this and like this. So like a saucer and like a dumbbell, right? It can be like this. So the structure will be like this. Spherical, like this, like this. But again, why? This is not deformed because the equilibrium shape is spherical. So these are possible vibrational excitations. Density is fixed. Density doesn't fluctuate that much. Density remains the same. Shape is being, you see, shape fluctuations. I am not saying that the neutrons are getting compressed or the protons are getting compressed. I am not saying that. What I am saying that neutrons as a whole, protons as a whole, they are vibrating. This is what I am saying. Prolate, now here protons and neutrons are behaving as different groups, but in this case all of them are working together. So it's not that this is a prolate due to protons, this is oblate due to neutrons. No, here you write it down. Here all the protons and neutrons, they are coherent excitation behavior. Okay, now this is isovector character and this is quadrupole character. Why I am saying this? So I will tell this later on when I talk about the mathematics of this. Just write it down. Any more questions? So without going into mathematics, we have just discussed the various physics from very basic point of views. Vibrational. It is easier to understand this structure.